Hi, what I've got here today is an MV216A DC voltage standard made by Electronic Development Corporation. The EDC was later acquired by Krohn-Hite. I think it was back in 1998, sometime around that time frame. So this DC standard has long been discontinued, and I think it has a vintage of about at least 30 years. I'm sure that many of you have seen a video made by Dave Jones, in which he did a teardown of the MV106A 106 voltage standard. So the layout of that voltage standard is fairly similar to this. It also has 6 decades, 1, 2, 3, 4, 5, 6, adjustable knobs over various voltage ranges. And by the way, the difference between the 106 and the 116, which a lot of people also have, is that the 106 has a 10 volts, 100 millivolts, and 10 millivolts range, whereas the 116 has a 100 millivolts, 1 volt, and 10 volt ranges. So for most of the users, especially for me at least, is like the range down to the 10 millivolts probably is just a lot of noise, because I don't really have any instrument able to measure the voltages in the nanovolt range. And also this unit has a temperature coefficient of roughly 5 ppm. So by the time you get down to the extreme low voltage range, the last few digits gonna be pretty much inaccurate. Nevertheless, you can use that to do some relative measurements. Anyway, so for the 216A, I think that for the most part is similar to that of a MV116, except that this unit, if you look carefully here, we have it says it's battery powered. It could be powered by battery. And as the name implies, it's a battery external powered DC voltage standard. So I think besides that difference, there probably are not that many difference to the 116A, but that was just my guess. Unfortunately, I contacted the EDC, and they don't have any manuals available for this particular model. So which means that your guess is as good as mine. We can take a look inside to see what is going on, but before I do that, I wanted to kind of let you take a look at how accurate this unit still is after 30 years. So here on the bench, I have the setup of a Keithley 196 6.5 digit multimeter, and now I set it to the its lowest range. I think is like 2 volts, 2.6 volts range. And now I'm here setting this voltage standard to a 1 volt output, and so the maximum would be 1.11111 when every knob is turned to 1. Now I'm outputting a 1 volt. So as you can see on the multimeter, that it is fairly stable, reading at 0.999971. Now, of course, this multimeter could be a little bit out of cal, and this thing definitely hasn't been calibrated for a long time. And I actually couldn't find a calibration sticker on this unit, so presumably had been in storage for an extended period of time, at least for the past 10-15 years. But anyway, regardless, as you can see, it's still very accurate, and we can dial into different voltages and take a closer look. So now I'm in the 1 volt range, and I want to increase it by 10. Oh, sorry about that. So this really should be 10. So that's your 1.1 volt. And now I can do 1.11. And let me just dial all these in. So that's the 1.111 volt range. And it does take a little bit of time to settle. as you'll see later that there's an output capacitor across these terminals. So it takes quite a significant time if the adjustment voltage is towards the lower end of the voltage. And let's just take a look at another range here. Let's move it to the 10 volts. Before that, let me change the my setting here. So the 10 volts, again, no problem at all. 11 point. So let me just turn this back down, and hopefully it will show very close to 10.000. As you can see, indeed shows a 10.000, and the last few digits do oscillate a little bit, but that's to be expected as we are down to the limitation of both of the instruments, actually, in this case. Because the last digit here, if you read here, is 10.12345. So this is 1, 2, 3, 4, 5. So that is corresponding to the least significant digit here. So if I do move that, as you can see, it does change to 1, 4, 1, 5. So it's not, it does change a little bit. But when it settles, that's when it counts, and statistically it also would have some error, margin of error on the last digit. But so let's if we can probably see more clear if we adjust the second but last digits. So as you can see that the value increases to 27 from 17 gradually. That is because the output capacitor across the terminals, making the finer adjustment very slow. So no problem at all. And again, if you want to do, let's change the range down to the microvolt range. So we can dial in, let's see, so this is our 10 microvolts, 1, 0, so let's go down to 1 microvolt, no problem, and 2 microvolts, 3, 4, 5, 6, yeah, so as you can see, it's extremely accurate, certainly more accurate than most of the instruments I have here in the lab. Now, let's so after this initial inspection and everything seemed to be working, let's take a closer look at the actual build of the voltage standard. So let me just turn it off and disconnect my. So let me let me just readjust the setting of the multimeter, and let me remove the cords here, and I'll move the unit back and we'll take a look. And before I open up the unit, I just want to show you that this one actually, when it's in standby mode, you can see the LED is actually on. So which means right now I have it plugged into my AC outlet that is on external power. So this external power LED is on, and there's a charging LED, so presumably you can put some battery inside, but this one doesn't seem to have any battery, so we can take a look later to see what is inside. But then you have this battery charging meter, so when it turns on, you can see that it goes all the way up here, so presumably it means that it's charging. So clearly, this unit was designed for field service of. So if I turn it off, that LED remains on. And similar to what Dave showed in his video, when you turn it on initially, this overload light would be on for a while, but it would turn off after a few seconds. So I think that's just a normal operation. And here's a look at the back of the unit. This one actually has a connector here. I assume that this is for the external power supply, but later we can take a detailed look. And here's the power cord coming out. So this one, you can have the 4 feet here, and the unit like this, typically these are for you to wind out the power cord. Also, you can put this, like standing up on the bench and without any problems. And I have already removed the screws on the back, so now I can just slide open this the top cover. Actually, this is something stuck here. Okay, now I can just slide it open. I need to move the camera before I can further slide this off the top. Just give me 1 minute. Now with the top removed, let's take a closer look at what is inside. And I'm going to hold the camera here so that we can take a closer look, and later when I'm explaining each part, I'm going to mount the camera back on the tripod so it won't shake too much. So as we can see that here is our transformer, and nothing is everything just soldered right here. I did unplug the power cord, but everything is just soldered in without like any insulation. So here is our the transformer, and the secondary just goes to this board and goes through this bridge rectifier. And what is interesting here that is different than the unit Dave showed, which was the MV106, is that we have a DC to DC converter here. And the reason they're using this DC to DC converter instead of a the 78 series for the plus minus power supply is that because we have the option of using an external power, and it will be pretty clunky if you require both the positive and negative. So, and also the battery option, you just have one battery supply the input voltage, and then the DC to DC converter would be converting a plus and minus, I think in this case is 15 volts to the circuit. And anyway, so we also see towards the back panel here, and you will see that this connector that we saw on the back, it has red and black purple. The purple is soldered onto the case, so that's the ground. So this is our external power coming in, and we have a fuse missing here, and I don't know what this is doing here, but because this one has a battery option, or it had a battery, this one is simply having the battery removed. There's no way for me to tell because I don't have the the user manual or the original unit. But anyway, so the only thing I can assume is that this fuse is for the internal battery. So somehow the battery, if you look at the open space here, so the battery was mounted here and would be coming into this unit via this fuse here. And then we have this 309K. This is a voltage regulator, and we have some filter capacitors here. And so the layout actually is surprisingly similar to, well, not surprisingly similar, because it also has 6 decades, and it does the same it provides almost the same functionality as the MV106 and 116. So I think it is reasonable to assume that the majority of the circuit actually does exactly the same thing. So here is that chopper amplifier, and in the unit Dave reviewed, it doesn't have this top, and it's just a daughter board soldered, plugged in directly to this main board. But here I think we have a, well, they did a little bit nicer with this case here. And we have some precision resistors here. These are 0.02 ohm resistor, and so that's pretty much what is on the main board. What is interesting is I just noticed, and I'm not sure how well you can see, is this IC here. This is actually an opto-isolator, optocoupler, so it's a 4N26. I don't believe on the model that they've reviewed had this opto-isolator, so presumably this is needed for the battery operation or some I actually can't see where the lead is going to, but yeah, so that's interesting. And here we also have this 4-terminal device. I'm not quite sure what this is, because it's clear. If you measure the resistance, it's clearly not a resistor, but either it has to be some, it's temperature coupled, these two things inside, or it has some other special use, whether it's a choke or something I don't know, but so that this one is clearly very similar to what Dave showed in his unit. And before I move on to the voltage reference, I just want to show you the front panel, and so the inside of the front panel. And this one is actually slightly different than the 116 or 106, in that a lot of the resistors are, instead of mounting directly on the switches, they are mounted on a board. So I'm not sure if this unit was mass-produced or it's just a handmade unit by unit, but clearly there's some variations. And here is that output capacitor I mentioned earlier. So that is what is contributing to the slow rise in voltage when you are in the down to the the microvolt range, because it does take time for that to charge up. And here are our switches. So this switch actually is not in that good shape. I might need to clean it a little bit afterwards using some kind of electronics contact cleaner. As you can see that it does have a little bit of, I'm not sure if it's rust or just dirt caked onto it, but yeah, so that's not good. But as you can see that it didn't, at least from our quick measurement, it does not appear to be affecting the performance. So here we have the very low resistance resistors. Here, these are the 20 ohms, and these are the 0.2 ohms rather. So the contacts resistance here clearly plays a big role, in, especially for the resistance ranges this low. And now we move to the middle, and you can see that where we go here. Okay, so here is that the voltage range switch. So presumably that one of these is adjusting the calibration for each of the range separately. And down here, these are the 0.02, 0.01 percentage resistors. And here is that meter that we talked about earlier, saw earlier rather. And here are some for the first decade. So excuse me. So let's take a look at the resistors here. So these are also precision resistors. Tolerance is about, well, the ones we can see is 0.025. So clearly, a unit like this, its accuracy is guaranteed actually by these precision resistors networks, and so that's pretty much the price you pay for this kind of calibration unit. For example, if today, even if you go to DigiKey and Mouser or some other like places buy these kind of precision resistors, you're going to cost you a fortune. Just for the resistors themselves, probably will be over $100. So it is a reasonable price if you pay, a couple of $100 for this kind of unit, even if it doesn't seem like there's much inside, but just the precision components inside, and that would definitely worth the money. And similar to the unit that Dave reviewed, this one also uses a similar reference Zener diode. So the diode here, you can see, actually this one is not mounted anywhere special. On Dave's unit, the Zener diode was mounted on a separate standoff where I guess they, soldered after the fact that the unit has been assembled. But this one is soldered in place just like any other components out here. And if you read here, it's calibrated at 7 milliamp, and the voltage should be reading 62201. So we can take a look later to see what the voltage actually is. What I am more interested in is the temperature stability of the reference here. I think we can take a rough look at what the actual stability is. So according to Microsemi's data sheet, and this particular, the 829As are rated at 5 ppm, the temperature coefficient. So, which is not that great for a precision voltage reference. After all, if you have the linear technologies LTZ series, those are actually rated at 0.01 ppm. But I suspect that these are actually hand-picked, and their stability probably is higher, far higher than the rated 5 ppm. But we can take a look in that shortly. So first, let me set the camera back onto the tripod, and we'll measure the voltage reference temperature, not the temperature, voltage reference voltage, to see what it is reading. So I decided to take a look at the voltage reference voltage, and as you can see here, I used 2 mini grabbers. You can't really see inside, but I wired on each of the leads of the 1N829 Zener diode, and so now I'm using this multimeter, and the other side clip onto this multimeter leads. So let me turn it on, and we'll see what the reading is, and we'll give it a few seconds to stabilize. So already, without any stabilization, it's reading 6.22, 007, 006, so it's very, very close to the 6.2201 that it was specified on the unit. And I'm not sure what the calibration temperature was, but presumably it was 23 degrees Celsius, as that was the standard back then. So as you can see that it's pretty safe to conclude that both of these are actually bang on. As you can see now, it gets warmed up a little bit, and that did change to 62.2209 and 07, 08, 09. So somewhere around there. So sorry, 008, 009. So somewhere around the 6.2201 mark. And what I'm going to do next is I'm trying to determine the temperature coefficient of this Zener diode. So to do that, what I'm going to do is have a very crude setup. Now I'm thinking is having a thermometer, somewhere near the vicinity of that diode, and I'm going to use a maybe a blow dryer, a blower or some kind of heater to heat it up gradually to see what the temperature coefficient is. And in the meantime, I'm gonna keep measuring the temperature and the voltage. So I'm going to record that, and at the end we can kind of do a very crude calculation of that temperature coefficient. So as you can see right now we're around 23 degrees. What I did was I put this thermocouple tucked right underneath that Zener diode. So hopefully it's close enough to measure the temperature. And now it's changing between 23 and degrees right around that area. And the voltage is somewhere like 006 to 009. So let's just say 008. It doesn't really matter, as that's accurate enough. So right now what I'm going to do is I have this, the hair blow dryer. So I'm going to set it on a low. This is probably not ideal because they're going to heat up other components as well. Also, it generates airflow, but I think for our purpose, it should be accurate enough. Should give us enough information to calculate a very rough idea of the temperature coefficient for that Zener diode. So let me turn this on. It's going to be noisy, but hopefully our experiment will run just for a few minutes. Okay, so now I'm going to gradually. So as you can see that the temperature is increasing, so is that the voltage reading. I'm just going to keep doing this until the temperature reaches about, I don't know, like, well, it depends on how fast it rises. Right, so let's just say 44.8. Well, let's, hang on. There we go, 49, 46. It's a little bit hard to control this temperature because I'm all over the place, and I really need to hold it very steady. So let's say we are set 47.5 and 26. So remember that number. So with our measurement data in hand, we can calculate the temperature coefficient of that Zener diode. So let's take a look at what we have here. So we have initial condition is 23 degrees Celsius, and the measured voltage is 6.22008 volts. And when we are done with measurement, our temperature was recorded at 47.5 degrees Celsius, and the voltage was 6.22027 volt. So your standard temperature coefficient is defined as Tc equals the delta V, your voltage difference, over the temperature difference times your reference voltage. So in our case, we have we just plug everything in, 6.22027 minus 6.220. Let me put it in here, 08 over 47.5 minus 23 times 6.2201. So this one really doesn't matter, as we'll just use it using the standard voltage that was supplied with the Zener diode as the reference voltage. So now let's use our calculator to take a look. So we have 6.22027 minus 6.220 008, sorry, 008. And we're gonna divide this by, in parentheses, 47.5 minus 23, and we want minus 6.2201. So it's the final result is roughly 1.25 times 10 to the minus 6 power. So this is actually, the 10 to the minus 6 is 1 ppm. So this is basically the temperature coefficient is roughly 1.25 ppm. So as you can see, this is much better than the rated 5 ppm for this type of Zener diode. Again, 1.25 ppm is still not very, it's not very low by today's standard, and many linear technologies voltage reference you can get it well under 1 ppm. So in some cases, for example, the LTZ1001, that voltage reference, as I mentioned earlier, can it had a heater built inside. So for that one, the actual voltage change is better than 0.1 ppm. But again, when designing a unit like this, a lot of the things have to be taken into consideration. I really appreciate the fact that the Krohn-Hite and the EDC build this unit so elegantly. I mean, it's so simple. It doesn't really have many parts that you cannot get in today's market. Yet it's been working for over 30 years and it's still in pretty pristine condition. So my hats off to those engineers who designed and built this unit. So what's the vintage of this thing? Well, we can find out. I'm not sure if you can read that, but if you look at the resistors, focus here, it's the 27th week of 79. So this one was actually built many 35 years ago. Wow. And let's just to verify that, let's find another component here. And I think we can find a this, let's see here, this resistor is the 27th week of 78. So clearly this one was built back in the 78, 79 time. Yep, so this resistor also is 78, last week of 1978. So wow. So this unit has been around for 37 years, and it's still, pretty much right bang on. And when you think about that, that's a remarkable piece of engineering product. A lot of the stuff we bought today, you can't expect it to run for more than a few years. But a precision instrument like this, it's been used and been stored, been abused, and yet 30 years on, everything is still pretty much, still a piece of a precision instrument. And I think one thing that we actually have this very nice unit is that the designer chose simplicity over complexity, and I think that's one of the design principles we need to adhere even today. So when you design something that is simple, fewer moving parts, then it can be expected to last a long time. Whereas if you design something overly complex, there are more parts that are gonna break, and so over the years you gonna see a much higher failure rate. But it still amazes me that even this simple design without an oven, this unit can maintain its accuracy over this long period of time. So let's now just for completeness, let me flip over the unit to take a look at what is at the bottom. I don't think there's anything, but just to see that how the pieces are put together. And as I mentioned earlier, because this unit was built such a long time ago, none of the things are meeting today's safety standard. And if you look at the connectors here, everything is exposed, and we do have an input fuse protection, but that is pretty much it. And even the ground pins are not, the ground connections are earth ground connections are not crimped in. As you can see, even though the terminal is screwed in, but the actual wires are soldered in. And if you just look at the components here, and you can see that all the pins are actually bent out of their original spacing, so that's not something that today's design you will see, but back then it was pretty popular, as all those PCBs were probably hand-drawn instead of routed by computer. So let's flip it over and take a look. Actually, before I flip it over, I just want you to see how particular each of the component was put in. If you look at this diode here, you can see that one pin is deliberately bent so that number one is much neater to solder it in. You don't have to bend it against the actual casing, so that you accidentally bend somehow shifted the die connection that can affect your performance. And so similar things you can see here, even this simple diode, and you can see that one pin is bent, pre-bent before it was mounted. So this attention to detail is very important in terms of achieving that level of performance. And here's another close-up shot. You probably can't see the part number, but that's where that Zener diode was mounted. And as you can see, there's really nothing special. I mean, it doesn't even have a dedicated standoff for that Zener diode, but it might have just been handpicked and measured and then put it in place. But that is the heart of this voltage reference. So I just flipped over the unit and took off these two screws, and the bottom unit also slides off right like this. So let me raise the camera and we'll take a peek inside. Actually, the best is probably for me to hold the camera by hand, as these angles are pretty tough to arrange. So as you can see, that's exactly what I expected. The bottom is really, there's nothing to it. It's just a tinned PCB, and what we see doesn't look like there were a lot of maintenance done to this board, except look at this. This is very interesting. And if you look at here, this I'm not sure how well it comes up in the camera, but clearly when they solder this, that's a capacitor on the other side. Either the soldering iron is not hot enough or something, and there's some like left over here. Also, it's not very well soldered. I might be touching up this later so that it doesn't fail down the road. But otherwise, it's just a pretty standard construction technique back then. And so here's the EDC, Boston, Massachusetts. And let's see, so this is the one that I was mentioning. This is the DC-DC, this is the chopper stabilized op-amp that on the other side. These are the standoffs where the other unit was, the other module was plugged in. And so I might, oh, look at this. Here's another bulge wire. It's basically connecting these two together. Instead, they could have just made that trace. But because these units are not mass produced, and I wouldn't be surprised that if they did just a couple of thousands of these units. But so it's very expensive to respin. Actually, they might even have done this just by hand. Again, here are some of the places where the soldering was not done very professionally. These kind of areas indicates that the soldering temperature was not high enough, so that when it melts, it actually didn't melt all the way. Either there's too much solder or things like that. But hey, it doesn't matter. It had been working for 30 years, and I believe it's going to continue to work for another 30 years. And here we can take see another look at these switches. And so actually I was wrong before. Not all resistors are mounted on the boards. So as you can see that these boards are for calibration, and these resistors are mounted on a separate board. But actually, those voltage divider resistors, those high precision 0005 1.9, those resistors are actually soldered directly onto the switch. So unit like this, the only part that might fail is that those switch connections, and definitely it's a good idea to make sure that those are clean and well maintained. Now there is there's some guidance on how to here you can see the terminals leading to the outside. These are probably most likely gold-plated terminals to make sure that the contact resistance are in check. And you need to be careful when doing your measurement, as these are 4 terminals. So the sensing terminal and the output terminal needs to be connected securely. For if you're just using 2 wires, otherwise the reading is going to be jumping all over the place, which is something that a lot of people tend to ignore or tend to forget. So that is about what I can see from this unit. And I think what I will do in the future, if I have time, is to figure out how do I add a battery unit inside, because that will be very nice. I can kind of use this as a just a portable reference. I can use it in places where you might not have access to electricity, and that's also one of the selling point of this unit initially, was that it can be made to use either battery or your mains power. But since I don't have the the schematics for this, I might need to do some testing, but it shouldn't be too hard, as I can already see where the voltage is coming in. I just need to verify what is appropriate voltage to supply to it. So that might be for another time, and when I get to it. So anyway, I hope you enjoyed the video, and if you liked it, please give it a big thumbs up, and I hope to catch up with you next time.